The sources outline a mathematical and physical journey that begins with the rigorous verification of vector calculus identities before applying them to the fundamental laws of gravitation. By moving from abstract position vectors to the interior dynamics of a planet like Earth, the narrative demonstrates how mathematical consistency allows us to describe the universe with precision. The verification of vector calculus identities across different coordinate systems serves as the mathematical bedrock for understanding physical fields as intrinsic, invariant entities. By calculating the divergence and curl of a position vector in Cartesian, cylindrical, and spherical coordinates, the sources demonstrate that the results, a divergence of 3 and a curl of 0, remain identical regardless of the chosen frame of reference. This coordinate invariance confirms that these operators are not mere mathematical artifacts but tools that reveal the fundamental nature of space, such as the uniform radial expansion of a position field or its irrotational structure. Such verification ensures that when these tools are applied to more complex phenomena, like the gravitational field, the resulting physical laws, e.g., Gauss's law for gravity, are based on robust, universal principles rather than the constraints of a specific coordinate perspective. Once these identities are established, the sources apply them to the gravitational field, revealing a shift from linear expansion to an inverse square attraction. In this context, divergence becomes a tool to identify mass. While the field is solenoidal, zero divergence, in the vacuum of space, it acts as a sink at the site of a mass, a relationship governed by Gauss's law for gravity. Furthermore, the verification that the curl remains zero even in gravitational fields confirms that gravity is a conservative force, meaning the work done within the field is independent of the path taken. The narrative concludes by examining the interior of a solid sphere of uniform density, such as the Earth, to show how these equations adapt to boundaries. Inside the sphere, the divergence becomes a non-zero constant, causing the gravitational force to decrease linearly as one moves toward the center, where the force eventually reaches zero. This complex transition from the decay of the exterior to the linear interior is brought to life through Python-based visualizations. As shown in the provided diagram, Python serves as the bridge that translates these mathematical examples into dynamic animations, providing visual confirmation of the field's radial nature and the total absence of rotational swirl.